Welcome back to Calculus for Economics. Today is Tuesday, April 14th, and we're going to talk about differentiating the natural exponential and the natural log function. So we were introduced to these two functions fairly recently, and then we saw some applications in compound interest. We're going to look at the calculus of these two functions today, which for us is basically going to mean the derivatives. We'll derive the basic differentiation rules for the exponential and the log, and then we will apply those in a few examples. So let's first look at the exponential. Uh, to get started, when confronted with a new function and you want to find out about its derivative, the only thing we really have is the basic definition of the derivative. And so that's what's going on here. The derivative of e to the x is the limit of the difference quotient. And you may remember the difference quotient here we call the arc function, the average rate of change function, f of x plus delta x minus f of x over delta x. And you take the limit as delta x goes to 0. We have to do this because none of our existing rules apply. Exponential functions are not power functions. They're not polynomials or rational functions. And so we really have to resort to the derivative, the definition of the derivative. To work with that a little bit, you can use some of the algebraic properties of the exponential function. So e to the x plus delta x, you can write as e to the x times e to the delta x using a property of exponentials, and then factor out the e to the x. And so that's what I've done here. And then the limit is as delta x goes to 0. E to the x is a constant as far as that goes, so it can pop outside the limit. So you have e to the x times this limit. The limit is delta x goes to 0 of e to the delta x minus 1 over delta x. Now that limit you can work with numerically, you can work with theoretically. You find that that limit is actually 1. I'm not going to go through the details of that, but that's what the result is. That limit as delta x goes to 0 of this creature turns out rather nicely to just be 1. And so the total computation has a result of just e to the x. That's kind of striking. The derivative of e to the x is e to the x itself. I'll just state for future reference that e to the x is the only function that has the property that the derivative is equal to the function itself. E to the x is very special in that sense. So that's worth knowing. What about the natural logarithm? Well, we can kind of piggyback off what we know about the exponential at this point, and also let's use a property that we know about the natural log. E and the natural log functions are inverses of each other. So it's true that e to the natural log of x equals x. Now, if I just differentiate both sides of that equation, the derivative of the left-hand side is just the derivative of e to the natural log x. We'll figure out what we need to about that in a second. But the derivative of the right-hand side is clearly just 1. So what is the derivative of e to the natural log of x? Well, we just saw that the derivative of e to any power is just e to that power. But the power wasn't just x. It was a function of x. So this is the chain rule. It says so the derivative of e to the natural log of x is e to the natural log of x and then times the derivative of natural log of x. And we know that has to be equal to 1. Now, e to the natural log of x, of course, is just x. That comes from right here. And so what we're really saying here is x times the derivative of natural log of x equals 1. Well, just bring the x over to the other side by dividing, and you get the formula for the natural log. The derivative of natural log of x is just 1 over x. And so, in summary, we have these two basic formulas for the derivative of the natural exponential, it's just itself, and the derivative of natural log of x, which is 1 over x. So you do need to know those two important formula. Let's take a look at an example. What if we wanted to take the derivative of e to the minus x squared? Well, here we're going to have to use the chain rule, just like we did in the previous slide. The basic rule says that when the exponent is just x, the derivative of e to the x is just e to the x itself. So the derivative of e to the minus x squared would be e to the minus x squared times the derivative of negative x squared. This is the chain rule in action. So it'd be e to the minus x squared times minus 2x, and we'd normally write that as minus 2x times e to the minus x squared. Similarly, what if you had to take the derivative of something a little more complicated involving the natural log, like natural log of 3x squared minus x plus 4? Well, again, you want to use the basic rule, which is the derivative of natural log of something is 1 over that something, at least when the something's x. So the derivative of natural log of 3x squared minus x plus 4 is just 1 over that something. But the something wasn't just x, so I have to multiply by the derivative of that something by the chain rule. And so we get 1 over 3x squared minus x plus 4, and then times 6x minus 1, which I could just write as a single fraction this way. So the chain rule is very common to come into play when looking at functions involving natural log and the natural exponential. If you want to see how the chain rule works sort of in general with the natural exponential, it's this. The derivative of e to the f of x power would be e to the f of x times f prime of x. The derivative of natural log of f of x would be 1 over f of x times f prime of x, or just f prime of x over f of x. Sometimes these are called the generalized differentiation rules for the natural exponential and the natural log. Let's look at some examples. Oh, but first, a couple of pro tips. It's always a good idea to simplify before you do the calculus, and that certainly holds true for the exponential and the natural logarithm. Simplify those if you can before doing the calculus. And then don't forget the other basic differentiation rules that often appear in problems involving derivatives of e to the x and so on. The product rule, sum rule, quotient rule, etc. Now let's take a look at some examples. Let's find the derivative of the natural log of the square root of x squared plus 1. So here is a prime example of where you want to simplify before doing the calculus. As usual, we write the square root as an exponent. So square root of x squared plus 1 is the same as x squared plus 1 to the 1/2. And then we use the property that natural log of something to a power is the power times the natural log of the something. So natural log of x squared plus 1 to the 1/2 power is the same as 1/2 natural log of x squared plus 1. That's one of the properties of the natural log that we saw a few videos ago. Once you've got it simplified, now it's a little bit it's quite a bit easier actually to take the derivative. The derivative of our guy is the derivative of the simplified version of our guy, and that's just 1/2 times the derivative of natural log of x squared plus 1. And now just using the sort of the generalized rule for finding the derivative natural log of a function, derivative of natural log of x squared plus 1 would be the derivative of x squared plus 1 divided by x squared plus 1. So that ultimately all simplifies into x over x squared plus 1. Let's look at another example. What if you had the cube root of e to the x? How would you find the derivative of that? Well, first you want to rewrite. The cube root of e to the x is the same as e to the x to the 1/3 power, and then use a property of exponents. E to the x to the 1/3 power is the same as e to the x times 1/3, or just e to the x over 3 power. And now differentiate. The derivative of e to the x over 3 would be e to the x over 3 times the derivative of x over 3. And that's just another example of our generalized rule for the natural exponential. And so that turns out to be e to the x over 3 times 1/3, of course, or just 1/3 e to the x over 3. One final example. What if we had this expression, the derivative of the quantity x times the quantity e to the x squared plus natural log of 1 over x? Well, again, start out by simplifying. E to the x, the quantity squared, is the same as e to the 2x by the same logic as used in the previous example. Natural log of 1 over x is the same as negative natural log of x. Why is that? Well, think of 1 over x as x to the minus 1. And then log of x to the minus 1 would be negative log of x. Now that we've got the simplified expression, let's differentiate. Well, here we have a sum rule, right? Or actually a difference rule. It'd be the derivative of x e to the 2x minus the derivative of log x, what I can just go ahead and write down. And then the derivative of x e to the 2x, I need to use the product rule there. So it's the derivative of the first guy, which of course is just 1, times the second guy, which is e to the 2x. So 1 times e to the 2x, or just e to the 2x. And then plus x, the first guy, times the derivative of the second guy. The derivative of e to the 2x is 2e to the 2x. So we're ultimately getting just 2x e to the 2x. And of course, I still have to subtract off my 1 over x. So the final result is that the derivative of that expression is e to the 2x plus 2x e to the 2x, and then minus 1 over x. So there you have 3 quick examples of differentiating with natural log and e to the x. I will have a homework out there that'll be due Thursday night on this topic. You'll have several questions like this. And in the meantime, I'll be working on our next video. We're going to actually start a new topic, partial derivatives, and that will be forthcoming probably Wednesday or Thursday. So in the meantime, if you have questions, as always, let me know. Email is the best way to reach me. And stay tuned, stay healthy, and I will speak with you again very soon. Y'all take care.